Hello and welcome back. We're here to talk about series and parallel circuits. We're continuing our discussion from last week when we talked about Ohm's law. We had simple circuits. Now we're putting those resistors into combinations. If you want a review of the ideas behind series and parallel, go back and look at the video from last week. You can see my, my intro. So save a little bit of time for you. Just don't have to do it again. Check out that video. I talked about series. I had a series circuit here and a parallel circuit there. We talked about calculating the equivalent resistances. Go check it out. The first thing we're going to do for this lab is we're going to build a series circuit with 3 resistors. So we'll have a battery, we'll have R1, R2, R3. Notice that they got progressively less neat as they went. We have 3 resistors. We're going to use our multimeter to make some measurements. We're going to measure the value of R1, R2, and R3. The same R1, R2, and R3 I had last time. R1, I even still have a little piece of tape on it, is manufacturer setting says 1,000, but we'll remeasure it. R2 is another 1,000, and then R3 is a 5.1K. So we're going to measure the resistances of each and write them down on our table. It also asks us, so we're going to measure R1, R2, and R3. We're also going to measure R12. The combination of R1 and R2, what is the resistance in this circuit from this spot here to this spot there? R23 and R123. We're going to measure all of those, and we can do that right now. Step 1, turning the dial to ohms, making sure it's in the ohm port. It is. Turn on my sensor. Actually, you know what? Got a little bit ahead of myself, didn't I? I don't have a circuit yet. Look at this, nothing. So I'm going to build my circuit. I'll start with the battery. I'm going to put them in order. There's number 1. There's number 2. Oh, that's number 2. And this one's number 3. Look at that. We have a series circuit. Now, if I'm going to measure the resistance of these, I have to remove the voltage source. It's not connected. I didn't finish it. There's a gap, so it's not actually running. When I close it, then it's going to be a full circuit and we'll have current going through. Actually, the current's going to be going that way. Did I make it right? I'm going to spin the battery around. You want the positive terminal leading into point to resistor 1. It doesn't make a lot of difference. It just will make a difference in the direction the current is going through the circuit. The overall resistance won't change depending on that. So now, when I close this up, the current will go in the direction that it is drawn up on the board behind me. But if I'm measuring the resistance, I don't want the resistors connected to the battery. That'll mess things up. So resistors are removed from the circuit. There's no external voltage attached to it. Now I can measure this. The knob is turned to the appropriate part of the dial. It's on ohms. It's in the right port. I turn it on and set to kilo ohms. Go across resistor 1. It says 1.00 kilo ohms, but I think we can do a little better than that. Go down to the 2K setting.
1.027, 1.028.
Okay. That's in kilo ohms. What does the table ask for? Just asking for ohms. So 1.028 would be 1.028 0.28, 1028 ohms. Next, R2.
1.022.
All right. $1,022 ohms. And finally, last but not least, R3. Well, that's not working. Look at that, it's a 1.
Well, that's because it's, you have it at the 2000 setting.
Yup, it's set to 2K, but 5K is bigger. So I'm gonna
5K
bump
is
it up
bigger.
to the 20K setting. Oh, I don't know if you can see that or not.
5.18.
5180 ohms. 5,180 ohms. All right, great. We got resistor 1, resistor 2, and resistor 3. Now I want resistor 1, 2, the combination of 1 and 2. So 1 and 2 together. I'm just going to put my, my leads on either side of resistors 1 and 2. It's going to send a current through and measure the resistance of the overall of those two. What do we expect it to be?
Well, series we add, don't we?
We do. So again, if you don't remember that, go back and check the video. We talked about it last week. But we just add them up. When they're in series, it's resistance of this one plus the resistance of that one. So I'm expecting it to be somewhere a little bit more than 2,000,
Yes.
2050-ish.
So keep your current setting.
Yep, if I go down to 2,000, it's probably not going to be enough.
That's right. 2.02.
2.02. $2,020 ohms.
Okay.
Let's take this year. $2.02. All right.
Okay.
And now we want 2, 3, so I'm going to bump it down. I'm going to put one lead on the front edge of number 2 and the back edge of number 3.
6.20. That, well, wait a second. That one, yeah, that one did nail it. Sorry. It did nail it.
6,200 ohms. Yeah,
Okay.
that'll go up. That's 20,
Right.
200, yep.
Yep, okay.
And now, last but not least, R1, 2, 3, the whole thing, the overall resistance. Another word for this, when you're talking about the resistance of the entire circuit, is the load of the circuit. Now this is going to be over somewhere in the 7,000 something
Yep.
range. So 20K, that should still
That
work.
should still work. 7.22.
7.22. 7220, 7,220 ohms.
Yes.
So next, we need to measure the voltage. The voltage across number 1 is going to be the voltage drop from this spot before R1 to this spot after R1. Remember that hill analogy we used a while back? The negative side, the negative terminal is the bottom of the hill, it's the low potential. The analogy is pretty good because we talk about gravitational potential, and if you're way up high, you have a lot of gravitational potential. If you're way down low, you have a little bit of gravitational potential. So up here at the top, at the plus, we have a lot of electric potential. Down here at the bottom, we have less. It's a potential difference. So this is the bottom of the hill, and that's the top of the hill. And if I go from here to here, it's like jumping off the cliff, where I can go around, take the path, and drop a little bit here, a little bit here, and a little bit here, and now I'm at the bottom of it.
So those are like stairs.
Yeah.
Okay.
To get you to the bottom. So we want V1, which is going to be across resistor 1. And we want V2, which is the voltage across resistor 2. We want V3, which is the voltage across resistor 3. So, quick question. We have some voltage total from our battery. If I was to find the voltage across 1, it's going to be less than the total, because I haven't gone all the way down the hill. I've only gone part of the way down the hill. Same thing with 2, it's only part of the trip. Same thing with 3, it's only part of the trip. But what if I add V1 plus V2 plus V3? That's the whole trip, right? It's going all the way from the top, all the way down to the bottom. So the sum of all three of those should add up to my overall voltage. So we're going to want to measure that too. We're going to want to know the voltage across the battery, which would be from the very start to the very end. And I think it has us check the halfway points too. V12, which would be from the start of 1 to the end of 2, and V23, which is the start of 2 to the end of 3. So I'm going to write those down, then you're going to write them on your table. V1, V2, V3, V12, V23, and V123. Do you remember how to do voltage measurements? I hope you do. I taught you last week, but if you don't, this is a good time to review. Step 1, make sure it's turned to DC volts on the dial. Step 2, I'm going to make sure it's on the right port, and it is. Step 3, it's going to be connected while the circuit is complete. There is current going through there right now. It's a complete circuit. There's current, and there are voltage drops, which we're going to measure. The voltage is the same when I hook the resistor inside of the detector in parallel with the section that I'm measuring the voltage of. So since I'm measuring the voltage across resistor 1, I'm going to hook the leads so that the meter is in parallel with resistor 1. So the leading lead, the positive lead is going on the front edge of resistor 1. The negative lead is going to the negative side of resistor 1.
.396.
0.396, and that's in volts. .396 volts. Forgive my bad handwriting. Now putting it in parallel with resistor 2. So positive side goes on the positive edge of resistor 2. Negative lead goes on the negative side of resistor 2. And we get
.394.
And we expect those to be similar because those are similar amounts of resistance. .394 volts. All right, so a couple pieces of logic here. Resistor number 3 is bigger. It's the biggest one. So do we expect the voltage drop to be bigger or smaller across resistor 3? V equals I times R. The current through it is the same. They're all in series. I is the same. R is bigger, so V is going to be bigger. Similar logic, but a similar result, but different logical steps to get there. The total voltage across this battery is going to be somewhere around 3. We measured that before. It's got two 1.5 volt batteries in it. It's going to be somewhere around 3, a little less than that. 2.87-ish, somewhere in that range. We've gone down about 0.4. We've gone down another about 0.4, which gives us about 0.8. We have another step to go, but we only have one more step to go, which leaves us about, if we started at 3 and we went down 0.8, about 2.2. So we have about 2.2 volts to go before we get to the bottom. So we're going to expect the voltage drop across this to be about 2.2. Let's find out.
Okay, about 5 times bigger.
And that's interesting because it's about 5 times as big as the resistance.
Okay.
That's outstanding. I love this stuff.
1. Overload.
Not big enough. So it was set to 2 volts, and I just walked you through the fact that I thought it was going to be bigger than that, but I just showed it. I proved it to be so.
2.01.
2.01 volts. All right, a couple more that we want to take. We want voltage across 1, 2. So positive end goes on the front edge of number 1, negative end goes on the back edge of number 2. So both 1 and 2 are in parallel with this, or this is in parallel with the series of 1, 2.
0.78.
Is that at all surprising to you?
No, but, whoops. I'm just wondering when you're going to say, I think I can do a little bit better than that.
I think I can do a little bit better than that.
Yeah.
Good point. I was so excited that it worked out the way I wanted it to go. This is about 0.4, this is about 0.4.
Yes.
The combination of the two of them is about 0.8.
That's right.
That's kind of nice. So you think we can do better, I think you're right.
Because,
I'm going to knob it down to 2.
yes. .792. And that's even closer.
It is. Outstanding. Now, number 2, 3. So we're going to put it on the front of 2 and the back of 3.
Sure. Oh, that's an overload, but V3 all by itself is an overload.
Yep, so we kind of expected that.
2.40. And that's kind of what we expect.
And now 1, 2, 3. All the way across all 3 resistors.
2.80. Just what I thought.
You rock.
And this is really cool because on like the second day of class, in 101, we talked about adding and subtracting significant figures. And this kind of shows it.
I love it when stuff like this comes together. All right, we got one more set of data that we want to gather. So we got the resistances and we got the voltages. Now we want to get the currents.
Yeah, we really need to.
Not what I want to.
Oh, well, if you want to, yeah, because
They're
it's...
going to have to be able to do this, and I don't want them to burn up my sensors.
Okay, and it is fun,
Well, heck yeah.
because this is the happiest place on earth.
If they were here in class, I'd make them do it, and I'd make
Sure.
them write it down. I don't know that there's a column in your lab, but it's worth writing it down.
Okay.
Why do you say they don't have to? What about this tells you that they don't need to?
Well, it's a series circuit, isn't it?
It is. It is.
And these resistors, they don't eat electrons and store electrons or produce electrons.
Yep,
So whatever goes in must come out.
yep. So we would really only need to measure the current once. And if we know V123 and we know R123, we know what the current's supposed to be.
That's right.
Because V equals I times R, we can figure out what I is.
Yes.
And that was correct, proper grammar. What I is correct.
Yes.
Okay. Step 1, turn the knob. DC amps, it's right there. Right there. Part 2, move the lead over to the milliamps slot. Part 3, wherever I'm going to be measuring the current, I disconnect that spot on the circuit so that I can complete the circuit in series with the device. We do not put the device in parallel with anything when we're measuring the current. You disconnect the circuit such that there is no current going through unless I connect it, reconnect it with this. That's important. Don't let it happen. All right, so where are we going to measure the currents? It actually tells you on here where you would put the sensor. So it's got one sensor here coming out of the positive terminal, and it calls that I0. That's
Okay.
the current coming out of the battery and going into R1.
Okay.
Then it has a current coming out of R1 and into R2, and that's I1. Then it has a current coming out of R2 and into R3, it's calling that I2.
Okay.
And then it has a current coming out of R3 and back towards the negative side of the terminal, and it's calling that I3.
Okay. So whatever comes out, that's what we're measuring, and we're being consistent.
Yeah, that's what it says on the paper, and I'm going to be consistent with
Okay.
that. I know the guy who wrote it. He's
Yeah.
standing by the camera, so I don't want to argue with
Well, I went to space camp 3 times.
him. That's 3 more than me, and I'm jealous.
Oh, yeah.
Okay, so let's measure I0. I got it coming out of the positive terminal and heading up towards R1. I've got the circuit broken right here, so there's no current running through it until I connect like so. Oh.
I'm getting a 0, 0, 0.
I'm thinking, oh no.
Now I'm getting
Good.
something. 0.380.
0.380, good. I0 is
0.380. And I'm gonna assume that's milliamps.
Milliamps.
Okay.
And what do we expect I1 to be?
Well, it'd be the same.
Yeah, we would expect it to be the same. Let's find
I
out.
haven't calculated it. Getting a 0 there.
I'm worried about the sensor. Thinking,
.380.
I'm not sure why it was not giving us a number, but.
I don't know.
All right, I2. Disconnect. And then reconnect it with the sensor.
.380.
I think I can remember that before I have to go write it up. I'm gonna get I3.
Okay.
Disconnect, reconnect.
.3, are you bouncing?
Yeah, hold on. I'm not getting a good connection.
.370. .377. 376.
Okay. It's not exactly.
379.
379. Not exactly the same, but it's probably a function of me not getting a good connection.
Yes.
To the two leads. But it's pretty darn close.
Yes.
So I2, 0.380 milliamps, and I3, 0.379 milliamps.
Cool.
Okay, so it asks, in theory, R123 equals R1 plus R2 plus R3. Do our numbers verify this?
Yes.
So you can add them up, double check, make sure. In theory, V123 equals V1 plus V2 plus V3. Do our numbers verify this? And again, add them up, make sure. At a glance, it looks pretty darn good.
Mm-hmm.
And the final in this section says, in theory, I123 equals I1, which equals I2, which equals I3. I think by I123 it's saying I0 equals I1 equals I2 equals I3, and I'd say that is a pretty solid yes.
Yes.
Okay, great. Now we're going to build a set of parallel resistors. Got our positive. Let's see. Want the positive emblem on that one, that's fine. This, for me, is fun. It's like playing with Legos, like I said.
Oh, yeah.
So R1, we go right there. R2 can go right here. R3 can go right there. We have the positive terminal, and in one way or another, it's going to connect to each positive side of all three of the resistors. And the negative terminal, in one way or another, is going to connect to all three negative terminals of the batteries.
Do you need a slightly longer one?
No, that's fine. I'll make it.
Okay.
It's not that hard to make them. I got plenty of little ones I can make do.
Okay.
Like I said, it's fun. You can be creative and find a way to make it work.
Okay.
What do you think?
Oh,
Lovely.
God. Yes.
Lovely. 1, 2, 3, positive terminal, negative terminal. All right, this table is a little smaller. So we've got a battery. And the way it's drawn, the battery is up top with the plus and the minus like that. It's coming out. We've got resistor 1, resistor 2, and resistor 3. Okay, so we're going to want to measure some stuff. with this. We have it, it's ready to go. We'll want to know the resistance of resistor 1. Well, we know that already. We measured it already from the first one. We haven't changed it, it's the same resistor. Same thing with resistor 2 and resistor 3. But I also want to measure the overall resistance of the whole thing. So I'm going to put the lead here and the lead here and find out the resistance for this entire parallel set of resistors. It's going to be resistance 1, 2, 3. What do you think, bigger or smaller than the individuals? Do you remember?
Well, it's parallel, so it's supposed to be smaller.
Yep, more paths means more ability to send electrons through, which means less resistance, which means a smaller R about it. All right, awesome. Then we're going to measure the voltages. To measure the voltage, I put the sensor in parallel with R1, so it's going to be in parallel with all of them, right? But I'll do them individually, and hopefully it'll show that. So we'll do R1, R2, R3, and then R1 across the whole thing. I should say we'll do V1, V2, V3, and then V across the entire thing. V1, V3.
Cool.
Then the tricky part, and part of the reason why I made it the way I did with these 2s, the small ones that I can take off, is because to measure the current through each of these branches, I'll need to disconnect that branch and find the current through that branch. Oh, that's an I1. And then the current through here would be I2. And then the current through here would be I3.
All right.
And I0 would be the current out of the battery. So,
Good stuff.
I'm happy with that. Let's get our numbers. We're doing resistances first. The battery is disconnected. There's no current going through it. I am going to spin the dial till I get to ohms. I'm going to move it to the ohm port. Not your home port, but the ohm port. And I'm going to do the resistance of the entire circuit. We're going to use the same resistances for the individuals as we did before.
So is Ohm one of those dead white guys?
I believe he is.
Okay.
I don't know much about ohm, to be honest.
Oh.
Meditative ohm, that's all I know.
Okay.
So, coming over here on the front side of the junction, so that it's, so the front side of the junction I was mirrored, and on the back side of the junction, so all 3 are within that parallel.
0.464.
0.464 kilo ohms. That's 464.
It is 464. Well, if we only had the 2000s, it'd be 500.
Yep.
So since we have that 5,000, it kicks it a little bit less.
When you have a set of parallels, if the equivalent isn't smaller than the smallest one, you've done something wrong.
Yes.
The smallest one is this one. This is smaller than that.
I like to think of resistors as cashiers at Walmart.
There aren't very many of them.
Yes, and even if you get a really bad one, like R3 is a really resistive cashier, it still speeds things up, even though they're really bad cashiers.
That's fair. That's fair. Okay, well good. Our resistor column is done. We kind of had a head start on that one. I'm going to connect the circuit. I'm going to spin the dial. I'm going to start it at 20 because we know that the battery itself is outputting about 2.8 from the last section. And I kind of know where this is going. So every single point on this side of the resistors is touching the negative terminal. Every single point on these side of the resistors is touching the positive terminal, which implies to me that the voltage drop across the battery is the voltage drop across each of those. But we're going to find out for sure. So I set it to the 20 volt setting because 2 would be too small. It is complete. I've got my leads. I'm going to attach on either side of the 1.
2.77,
Attached to the 2.
2.77,
Attached to the 3.
2.77,
Attached to the battery.
2.77.
Whew. I love it when it works. 2.77, 2.777, 2.77, and 2.77.
All right.
All right, time for some currents. The first current we're going to measure is right out of the gate, the positive terminal. So I'm gonna unhook the circuit. There's a gap. It's not complete. I'm gonna complete it with the circuit, or with the meter. Move this over to the milliamp hole. Turn the dial to DC amps. Do we expect the current to be bigger or smaller than it was before?
Bigger, because those light bulbs got bright when they were in parallel.
Heck yeah. So the equivalent resistance of the parallel set is smaller than the smallest one. The equivalent resistance of the series set is bigger than the biggest one because you're adding them all up. There's much less resistance than there was before, so the current's going to be bigger. I hope. It should. So, reconnecting the circuit. Here's the gap. Put the positive lead on the positive side, the negative lead on the negative side.
5.41.
5.41 milliamps. I'm going to reconnect that part, but I'm going to disconnect the next one that I'm going to be measuring. That's the branch with R1 in it.
2.5.
One more.
2.64.
Now we're talking. 2.64 milliamps. Reconnect R1, but disconnect R2.
2.64. And that makes sense, they're about the same resistance?
Yeah. All right, question.
Whoa, that ate up just about all the current, because that's like 5.28.
So, question. If a car pulls into an intersection, assuming it doesn't get into an accident or anything, that car pulls out of the intersection, right?
Yeah.
All right, good. If two cars pull into an intersection, no accidents, no stopping, how many cars pull out of that intersection?
2.
Okay, so as Professor Ashcraft was indicating, so we got cars pulling into this intersection. Some go this way, some go that way. The total amount has to equal whatever came in. So if some are going this way, then there's going to be less going down this way. Okay, now we get to another intersection. We have some coming in, some are going to go this way and some are going to go that way. It's going to be even less going through. Now, this intersection has very low resistance, comparatively, 1/5 of what this one is. It's a small one. This one is also a small one. This is a big one. Do you think a lot of electrons are going to go through the one with lots of resistance, or are they going to go through the easier paths? More are going to go through the easier paths. So I expect this to be a relatively small number for the current. Let's find out. Disconnecting R3, reconnecting R2, completing the circuit with my meter. 0.52, but I can get better. Can you see that? I can't see it.
Oh, sorry, 0.522.
There's a little glare on it from that angle.
Yes.
0.522. Okay. So it asks, in theory, 1 over R123 equals 1 over R1 plus 1 over R2 plus 1 over R3. Do our numbers verify that? Well, that's up to you to find out. I certainly hope they do. In theory, V123 equals V1 equals V2 equals V3. That one's pretty obvious. I'll still leave it up to you to figure it out, but that one looks pretty good. In theory, I123 equals I1 plus I2 plus I3. That's what we were just talking about. And again, looks promising, but you better double check it. I don't know.
Can we do I0 one more time?
Sure. I know Professor Ashcraft's way better at mental math than me, sir.
So I'm afraid that I might have read it wrong.
5.78.
5.77.
All right, so we checked our numbers, and I think I had a bad connection when I did I0. So remeasuring I0 here, we have, what is it, 5.78?
5.78?
So we're going to fix that. For I0. And that actually comes out a little bit better, I think.
Yes, it does. Much better.
All right, we have one more circuit to build. We're going to build a combination of both series and parallel. We've done one like this in the past. We've got our positive terminal, our negative terminal. It's going to come out. There's a junction. It's going to split. We have a resistor here, and a resistor here. It comes back together. This one has them labeled B, C, A, B, C, A, B, and C.
Yeah.
This one is, well, I'm going to stick with what we've got. This is going to be R2,
Sure?
and this one's going to be R3.
Good.
And this one is R1. Back up to the battery. Yeah, making sure the numbers are right. 1,000. Yep, we're good. And we're asked to find the resistance, the voltage, and the current through each of those and through the circuit as a whole. So, great. Resistances are good. They're not going to change, but the circuit as a whole is. The voltages we're going to have to measure. And the currents we're going to have to measure. Now the table's set up a little bit differently. It has I1, I2, and I3, and then I of the entire circuit. So I1, 2, 3. So 1, 2, 3. It doesn't have an I0. It just changed the format, that's all. Okay, now I gotta build. I think I got it.
All right.
What do you think? Looks good?
Yes, it does.
Okay, check it out. Put that on there and we've got a complete circuit. We've got the current going through. I know the resistance of each individual, but let's find the resistance overall. Change the plug to the ohms, turn the dial to the ohms. Resistance from the start of the set of resistors to the end of the set of resistors.
1.875.
1.875 kilo ohms.
Yep.
1,875 ohms.
Do you have any other measurements to do, such as the ones in parallel, or is that all they want for the...
All they want on the table is the totals.
That sounds great.
All right. Now I'm going to complete the circuit, and I'm going to measure the voltage drop across each resistor. And again, they don't want it across the parallels.
Okay.
So I'm going to turn the dial to volts, DC volts, and I have it set to the 2, but we'll find out if that works or not. Go across resistor 1. Sorry, guys.
1.531.
Okay. Going across resistor 2.
1.274.
What do we expect resistor 3 to have?
Well, that's in parallel with 2.
So we expect it to be the same.
1.273. It's certainly within measurement error.
Yep. And now over the entire set.
Oh, you mean how V1 and V2 are in series, or how V1 and V3 are in series?
Or just across the battery.
Yeah. Bigger than 2. Still bigger.
Oh, I went the wrong way.
No problem. 2.80.
Yeah, that's kind of what we thought. It's the same batteries, right?
It is.
All right, now to do the current, this is where the danger comes in, so I'm going to be particularly careful when measuring the current. Going to move the plug over to the milliamps, going to move the dial around to the current. Number one, so we want to pull the output of resistor 1, disconnect it. It is now disconnected, the circuit is broken. I will reconnect it using the meter.
1.46.
Think we can do better?
Let's see. 1.412.
1.412 milliamps. Reconnect that. I'm going to, now for number 2, disconnect the output of number 2, reconnect the circuit using my meter.
1.160. Now, I3 should be different.
Disconnect I3.
It's got the same voltage, but it's got a lot higher resistance.
So I'm thinking it's going to be a smaller current.
Okay. .23.
All right?
Well, can you get better?
I don't think I can. The next one is 2.
Okay. We should have.
We should.
Yeah, we
It
should
was
have
giving
3
me a 0.
sig figs.
Yeah. It was giving me a 0, but maybe I just didn't have good connection. There it is, yep.
.238.
.238 milliamps. And last but not least, the output of the battery.
Well, that should be the same as I1.
Yeah, it should. Let's find out. Oh, got them backwards.
1.408.
Yeah, within .04.
Yeah.
0.004.
Within measurement error. All right.
All right. I believe that is all we have for the series and parallel circuits lab. We've explored series circuits. We've explored parallel circuits and a combination circuit. You're going to want to take a couple minutes to check and make sure that the same things that we expect to happen are actually happening here. It doesn't ask questions about it here in this lab, but I think I'm going to probably ask you questions about it at some point, so it's worth looking at the data and seeing if the data does work the way we expect it to. So are the currents that are supposed to be the same, are they actually the same? Looks pretty good. Is this the equivalent resistance for the circuit as I build it? Well, that's going to be on you. You're going to have to calculate that. And just, hint, hint, nudge, nudge. I'm going to give you a quiz. It's going to ask you to do this, filling in the blanks theoretically. So make sure that you're able to do that.